This time we study exponential I theta, where theta is a real number. To, to consider this, we'd like to extend the region of the argument. Exponential x is defined for any real number. However, we would like to extend this one to complex plane. Z is a complex number. And what is the complex number? This is x plus I, y, and both x and y are real numbers. Okay, and what is I? I is the square root of -1. In general, complex number is a solution for the quadratic equation of real coefficients. And in case we have discriminant of, for example, ax squared plus bx plus c equals 0, we complete the square. B over ax plus c equals 0. We complete the square by using this method, b over 2a squared plus c minus ab squared 4a squared equals 0. We find that, what's that? We divide everything by a. We assume that a is not 0, plus b over 2a squared minus 4a squared in the denominator, b squared minus 4ac equals 0. We know a squared minus b squared equals 0. It is factorized into a plus b and a minus b. So we rewrite this one as a square root and square. Then x plus b over 2a equals plus minus square root of b squared minus 4ac over 4a squared. Simplifying with this result, depending on the sign, you know this one is a positive definite, but it changes its sign depending on the relative values of a, b, and c. So this is called the discriminant. If the discriminant is negative, we have a square root of -1 factor. That is called the pure imaginary number. So in general, the solution of a quadratic equation for real coefficients is a complex number. So we'd like to extend the region of x from real number to a complex number. And once you know the insert the complex number, then it is very convenient to compute the many physical variables. So you'd like to show this using the same method that we used to derive the Taylor series expansion, using binomial expansion and the definition of the Euler number. Okay. I don't have to explain in detail because what we have done already is the same, except that x is replaced with the z. So again, in terms of the power series in z, that is a complex number, we have exponential z is defined very well. I'd like to know whether this function is differentiable or not. We say a function is a complex number, a complex variable, this function is the differentiable, then we use the different terminology, analytic. Analytic is nothing but the differentiable. However, we know that function exponential x is defined only a single real number. So when we take the derivative of the exponential function, we choose a point and we approach to a fixed point. And there are only two directions. One direction from some value bigger than this. So from 0 plus on the positive part, and from the left side we can approach x0 by x0 minus 0 plus, or x0 plus 0 minus on the left. This is on the right. So when the derivative from below and from above, they are the same, we say we have a single derivative at a fixed point. Unlike the severe variable case, exponential z is defined on a complex plane. We have x and iy. We say it is a real part x plus iy, then this is called the real part of z, and this guy is called the imaginary part of z. Okay, so we have complex plane that is very similar to the two-dimensional Euclidean space, and the derivative at a fixed point at z0, that is x0 plus iy0. This one, we can follow any kinds of path. So the constraint of differentiability, that is analytic, the function complex function is analytic, then all of the derivative on the plane, any path will give the same value. So the constraint of analytic structure of a complex function is very strong, and the result is very simple. But it is not always true that the functions defined in real variable is analytic. The special cases are polynomials and exponential function, sine and cosine. They are analytic function. So the title, Analytic Continuation, is using the differentiability of a real variable function, we'd like to extend the region in which the function is defined from the real number to complex number. So that is usually said the extension of this region of definition from the real number set to the complex number is called analytic continuation. So once you know the special feature of this derivative, if you obtain a derivative in the real variable case, then in general, if the function is analytic, the derivative still exists and with the same shape. So we can compute the derivative with the same logic. Finally, our exponential function defined in the complex plane has exactly the same value as what we have obtained in the real number case. It is also true that integral power is a non-negative integer. This guy's derivative is again n z to the n minus 1. Everything is true. But it is not true for non-integral power, and even in the case when we have 1 over z, something like that, it is not differentiable as z approaches 0 because the function is not defined at all as z goes to 0. The functions like this polynomial, the sum of these powers, and this exponential function, and we should find that it is also true for the sine and cosine. They are differentiable, analytic, on an entire complex plane. So we say this kind of functions are entire function. G to the nth power, n is a non-negative integer. We can make use of binomial expansion, and the leading piece is this that has h cancels, and remaining pieces all have h squared or higher. So divided by h, they vanish. Okay, there's a mistake. This should be shifted by 1. Every factor shifted by 1. And it should be n minus 1, n minus 2, n minus 3, something like that. So simplify exponential I theta. We know exponential I theta can be computed by making use of this power series expansion. We have shown that this is identical to each other. Why don't we substitute I theta for a z? And we can sum over k, and the k runs from 0 to infinity. So why don't we choose even numbers and odd numbers separately? And we divide this one into two pieces. These are 2k, so 0, 2, 4, 6. 2k plus 1, 1, 3, 5, 7. So to the infinity. We know I squared is just minus 1. So I to the 2k is minus 1k. I to 2k plus 1 equals minus 1kth power multiplied by I. Therefore, these two sums can be simplified in this manner. And perhaps you must have learned that this one is the Taylor series expansion of cosine, and this one is the Taylor series expansion of sine. Therefore, if we have I theta 1 e to the I theta 2, and actually law of exponent will give this, and you have cosine theta 1 plus theta 2 plus I sine theta 1 plus theta 2. Okay, using this one, actually you can find addition formula of cosine and sine. Why? How? Cosine theta 1 plus I sine theta 1 multiplied by cosine theta 2 plus I sine theta 2. What is the real part? Cosine theta 1, cosine theta 2, and square this sine. We have I squared minus sine theta 1, sine theta 2. So this is the real part. That is the same as this. And then what about the imaginary part? We have a single I, this guy, cosine sine, cosine theta, sine theta 2, sine cosine plus sine theta 1 cosine theta 2. This is multiplied by a single I, therefore it is identified like that. So addition formula for the sine functions and cosine functions are completely obtained using this technique.